Good afternoon, everyone. Today we're going to talk about matrix algebra. A matrix is a rectangular array of numbers organized to row and columns. And we're going to start with the ERO, which is elementary row operations. These techniques are used to manipulate a matrix. And the first way of manipulating a matrix is swapping two rows with each other. And here's an example. So we're going to draw this. Row 1 is going to be 2, 1, 1. And row 2 is going to be 1, 0, 1. And row 3 is going to be 3, 2, and negative 1. And then we draw R1 here and draw an arrow between them, two-sided to R2. And this way it means that we're swapping R1 with R2. And it's going to be 1, 0, 1, 2, 1, 1, 3, 2, and negative 1. This is the first way of using the ERO. And then we have multiplying a row by a non-zero. So we'll get an example. We'll draw a row 1, 3, 1, 1. This is going to be row 1. Row 2 is minus 1, and 0, and 2. And then we're going to draw 1, 1, and 1. And this is our array. Then we multiply it with 1 over 3 R1. This is just an example. It's going to be, we're going to multiply R1 with 1 over 3. So basically it's going to be 1, and then 1 over 3, and then 1 over 3. And we're going to have row 2 as it is, and row 3 as it is. And then we have the final way, which is adding one row from another to eliminate the variable. So we will have an example over here, which is going to be row 1 is 1, 0, 1, row 2 is going to be 2, 1, 1, and 3, 2, and negative 1. And then we draw an arrow between them, and it's going to be 2 R1 with plus R2. Well, here, R2 is the one that's going to be manipulated. It's going to be written at the end. So we're going to have row 1 is going to stay the same, and row 3 is going to stay the same. We're only going to change row 2 as written here, which is this process that we wrote. And then we're going to do 0, it's going to be R2, minus R1, sorry, plus R2, it's going to be 0, 1, and negative 1. And this is the ERO, elementary row operation. We continue with REM, row echelon matrices. There are 3 properties which will make it to RREM, which is row reduced echelon matrix. So the first property is consists of at least a non-zero row and the leftmost non-zero entry in every row. So this is an example. It's going to be 1, it's going to be 1, 0, 0. We have one non-zero in this row. And the second row we have 0, 1, 2. We also have here non-zero as well in row 2. And we have a leftmost non-zero. So this one here and here. And then row 3, we're going to have the 0, 0, 1. This is the first property. The second property, the leading one in the lower row is further to the right than the row above it. So we're going to get an example. Do this. We start off with 1, 0, 0. That's in row 1. Then here it's 1, so we make sure there's a 0 under it, and then we put the right. Then it's going to be here 1, 0, 1, and then there's a 1 here, so we can't put it here. So we put a 0 here, and we can't put it here as well because it's going to be the most upmost right. So it's going to be 1 here. That's the second property. And then we have rows consisting entirely of zeros are at the bottom. So if we have a row that is fully at the bottom, it's going to be looking like this. Row 1 is going to be 0, 1, 0, and then it's going to be 0, 0, 1. As we said, the rightmost should be the one next one, but because we have a 3 array, so it's going to be 0, 0, 0. And then we have the RREM, which is row reduced echelon matrices. In every column that contains a leading one has a 0 everywhere else. So we're going to take this as an example. Column 1, 2, 3, and 4. Okay, so we're going to have 1, 0, 1, 0. So we can't have 1 here, so it's going to be zeros here. And we can't have 1 here, so it's going to be here. Okay, then here we can't have 1 because we already have 1s, so we put 0 and 0. Here we don't have a 1, so it's going to be 1, 0. And this is the RREM.
Hello everyone, this is Noor Uddin, and today we're going to be explaining how to get the determinant of a matrix. Here we have a 2 by 2 matrix, and to find the determinant we're going to basically multiply A with D and subtract it from B multiplied by C. And we can apply this on this example right here. It's basically going to be 1 multiplied by 4 minus 2 multiplied by 3, which is 4 minus 6, which is negative 2. However, in a 3 by 3 matrix, we're going to do the same thing, but in a different way. So for example, to find the determinant of matrix A, which is a 3 by 3 matrix, we're going to take A1 and put it right here, and then we're going to cover the same row and the same column as A1. So whatever is going to be left is going to be B2, B3, C2, and C3. So we're going to do the same thing as we did right here. It's going to be A1 multiplied by B2, C3 minus B3, C2. And then we're going to do plus, minus, plus, and so on. So it's going to be now A2's turn, and we're going to cover the same row and the same column of A2. And whatever is left is B1, C1, B3, C3. So it's going to be A1 multiplied by, or minus A1 multiplied by B1 times C3 minus B3 times C1. Now it's going to be plus, as it's plus minus plus. So we're going to cover the same row and the same column as A3, and whatever is left is going to be B1, C2, B2, C1, plus A3, B1 multiplied by C2, minus B2 multiplied by C1. And this is how we determine the determinant of a 3 by 3 matrix. Now, here's an example on how to find a determinant of a 3 by 3 matrix. We're basically going to get A1, which is 1 here. It's going to be 1 multiplied by B2, C3 minus B3, C2. So 5 multiplied by 9 minus 6 multiplied by 8 minus A2, which is 2, multiplied by B1, C3, B3, C1, 4 multiplied by 9 minus 6 multiplied by 7, plus A3, which is 3. And then we're going to do the same thing. 4, 8, 5, 7, 4 multiplied by 8 minus 5 multiplied by 7. And then you put all of this in the calculator, and then you get the determinant of a 3 by 3 matrix.
Hello, my name is Mahmoud Abdin, and today I will cover the inverse matrix topic. To solve this inverse matrix, we're gonna solve this one by using ERO to get an RREM matrix, which is the same as this one. My way of solving this is I'm trying to get zeros. And on here, that's number 1, then 2, then 3, then 4, then 5, then 6. And these 3 are gonna be 1s to solve the same as this. Step number 1, I'm gonna flip R3 with R2. R1 stays the same, and R2 and R3 switches. Okay. Step number 2, to get this as a 0, we're gonna solve it as negative 2 R1 plus R3. So row 1 stays the same and row 2 stays the same, and this one's going to become 0, 0, 0, 0, 2, and negative 1. And the inverse is going to be negative 2, 1, and 0. Step number 3, to get rid of this 2 to become a 0, we're going to solve it as negative 2 R2 plus R3. So row 1 stays the same, and row 2 stays the same, and row 3 changes. It's going to be 0, 0, 1, negative 2, 1, negative 2. So now next step is we're going to try and get this negative 1 as 0. So we're going to do R3 plus R2. In this case, row 3 doesn't change it, and row 1 doesn't change it. And this one's going to be 0, 1, 0, and its inverse is going to be negative 2, 1, negative 1. Now the next step, to get this as a 0, we're going to do R2 plus R1, where row 2 and row 3 do not change. 0, 1, 0, negative 2, 1, negative 2, negative 2, 1, negative 1. This row changes. It's going to be 1, 0, 2, negative 1, 1, and negative 1. Now we need to find 0 for this. But we're going to do negative 1, R3 plus R1 twice. You may ask why, but now you will see. So negative 1, R3 plus R1. First of all, row 3 does not change. negative 2, and row 2 does not change. 1, negative 1. But this one is going to be 1, 0, 1, and its inverse is going to be also 1, 0, 1. But in here you can see this one is not RREM as shown in here. So to get rid of this one and it becomes a 0, we're going to use negative 1 R3 plus R1 again. So it's going to be 1, 0, 0, and row 2 and row 3 does not change. Negative 2, 1, negative 2, 2, 1, negative 1, and this one becomes 3, negative 1, negative 1 and 3. After solving, we find this one becoming RREM by using ERO. So on the right hand side is going to be our inverse matrix. So this one is A. Our final value is going to be A to the power of negative 1, which is the inverse, which is going to be 3, negative 1, 3, 2, 1, negative 1, negative 2, 1, negative 2, as we solved before. Thank you.
Hey everyone, today we'll be also explaining the eigenvectors. For the eigenvectors, we have this rule: function lambda is equal to the absolute value of lambda times the identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, minus A, the given matrix. So we want to find the corresponding eigenvector for the lambda 3. So how do we find this? First, we write our formula times the given matrix A. Then we proceed with the solving. Lambda minus 1, negative 1, negative 2, 0, lambda minus 2, negative 2, 1, negative 1, and lambda minus 3. And if you proceed with the calculations, like we learned before, the final answer is going to be lambda is equal to 1, 2, and 3. Therefore, lambda 3 is equal to 3. The next step will be to substitute lambda in our formula with 3. And of course, we're going to use this rule. Lambda times identity matrix minus A times X is equal to 0. So what we're going to have is lambda times the identity matrix, which is this one. So all times X. We're going to use is equal to this matrix actually, 0, 0, 0. So we're going to use our previous information, the REM and the transformations, and we're going to put 0 next to this matrix. So now we substitute lambda with 3, and we start solving. The next step, we're going to put 0 next to this matrix, and we're going to turn this matrix into its REM form. So after reaching this form, we're going to find the number of solutions. How do we do that? So we get the number of non-zero rows in the original A matrix, which was 1, 1, 2, 2, 2, 2, 1, 3. As we see, the second row does not have a leading one, so that's 1. That's 2 rows here. And if you solve A, you're gonna notice that it only has 2 rows with leading ones, and the other will be just zeros. For this one, we also have this row, all zeros, and we have 2 rows with leading ones. So PA is equal to PAB, which is equal to 2, which is less than the number of variables, which is equal to 3, as we have 1, 2, 3 columns. So we're going to write let x be the free variable, let x3 be the free variable. Why did I choose x3? Because it's present in both. So what we're going to do is x1, like here, minus x2, plus 0x3 is equal to 0. Down here we're going to do x2 minus 2x3 is equal to 0. So this one means that here we can see that x1 is equal to x2. And here, x2 is equal to 2x3, which is equals to 2c. Sorry, 2c. Therefore, that means that x1 is equal to x2 is equal to 2c. X which is equal to x1, x2, x3, is in fact equal to 2c, 2c, and c, which is equal to c, 2, 2, 1, where c tends to all real numbers. So therefore, the eigenvector, the third eigenvector, which is for when lambda equals 3, is equal to 2, 2, and 1. Yeah, and that's it for the eigenvalue.